Hey dudes, Dude the Builder here, and in this episode of Zig in Depth, we're going to continue our exploration of Comptime in Zig. And the first area that we're going to look at is when you have code that can easily be determined, that is compile time known. For example, we're defining here this constant condition. We're setting it to false. So the fact that it's a constant, and we're setting it here to a literal value right there in the source code, is basically a guarantee here that we are dealing indeed with a compile time known value that cannot change. And the compiler can detect that, and if we have this type of code here that's performing control flow based on that value, since the value is compile time known, this evaluation will be at compile time. And since the compiler knows here that condition is false and it'll always be false, it knows that it will never have to evaluate this branch of the if, okay? And that means that we will not get this compile error, okay? Even though this would normally trigger immediately a compiler error if the code being evaluated reaches this line here, line 9. But since the compiler can see that this is a compile time known value and its value is false, well, this doesn't have to be evaluated, okay? So that's one example of how seemingly regular Zig code can be indeed Comptime code, Comptime evaluated, and thus improve the performance and reduce binary size of our programs, okay? Now, the other aspect of Comptime that we want to take a look at here, it's what's known as an inline for. If you think about it, a for loop has to, by nature, be a runtime control flow structure, because basically when the program is running is when that for loop is going to be executing each of its iterations, okay? But Zig also provides what's known as an inline for, which is evaluated at compile time, and that code is transformed, basically performing what is known as unrolling the loop. And what that means is that anything that has to do with compile time values is going to be evaluated and removed, replaced with the results of those evaluations. And the loop would basically, since here, for example, we're looping over the elements of nums, and nums has 3 elements here, 2, 4, and 6. Well, this loop would be enrolled to basically three executions of just this line here, which increments sum, okay? And here, since it's an inline for, and that requires to be in a Comptime context, this means that we can deal with types directly, and that's what we're doing here. We're setting this constant t, switching on I, okay, which is going to be each of the elements here in each iteration, and depending on I, we're going to set t to one of these types, okay? So we're returning basically here from the switch a type, either F32, I8, or bool, okay? If it's any other number, we know that it can't be any other number because we defined the array literally here with the literal. So we use unreachable here because we know this prong is unreachable. Now, after determining which type t will be, we call this function here type name length, which let's take a look at that. We have down here after main, and this function, as we saw before, has a Comptime parameter t that has to be a type, and it returns a usize. And basically what it does is it calls the built-in type name on the type t, and that returns a string, or basically an array, sentinel terminated array, as we saw how Zig defines the type for literals. Well, since this is all Comptime known, well, it'll be also that type of string. And we access the len field to obtain the length of the name of this type. Okay, so that length is going to be added here to sum, and that's basically these are the calls that are going to be left over after the compile time evaluation and unrolling of this loop. It's basically like if the sum increment was called 3 times, okay, with the result of type name length. So we can see here one of the advantages of dealing with inline for is that indeed we can do inside the for the different operations that are only allowed at compile time, like manipulating types directly. Okay. Now what we're going to look at is the inline while. The while loop can also be inline, so it can also be evaluated in a compile time context. Here we're resetting sum, and here we're seeing for the first time, aside from compile time function parameters, we can also use the comptime keyword to declare a variable to be comptime. So if we have a constant that has a compile time known assigned to it when we initialize it, that's basically a compile time known value. But a var usually is a runtime known value because it can change. But if we declare it like this with the comptime keyword, we're basically requiring that all loads and stores of this variable are going to happen at compile time. So that means that we can use variables at compile time, given that when we define them, we use the comptime keyword. Here we see how by adding the inline keyword to the while loop, we can then basically do pretty much the same that we were doing in the inline for. We're first setting t, switching on I, okay? And then we're incrementing sum with the length of the type name of t. Now what we have here is some debug print statements that are going to be testing out what we're going to be looking out further down in this file is a series of functions that we define to compare the difference between using an inline for and what we're going to see now, which is an inline switch, and not exactly the switch itself, but you can inline the prongs of a switch, and we're going to take a look at that now. To demonstrate this, we're going to define a couple of struct types here. First we have A, capital A. It's a struct, has a field A and B. B is optional, okay? And we have here a function, a declaration of a function called impl. It's empty because all we need for this demonstration is that the function be declared or defined inside the struct. And here we have a struct called B. This one also has 2 fields, A and B, but none of them are optional, okay? They're both U8s, and we don't have any function definition, okay? Now, the first function that we're going to take a look at is this is opt using a for. This is basically going to determine if a field at a given index is optional. And what we're going to do is we give it a type, okay? And we give it a field index, and it'll return a bool. Now, once again, since we're dealing here in a comptime context, here we have this comptime function parameter, we can deal with types and their information. So we're using this built-in type info, calling it on t, and that tagged union that we get back has a struct field, which is what we're expecting to be passed in here as the t type, a struct. And of that field, of that struct field of the tag union, it's a struct itself, and it has a fields field, which is an array of the fields of that struct. Okay. Now, here we have the inline for, and we're going to be iterating over those fields. We're also going to be using the index because we're going to compare with the index that was passed in here. Okay. And what we're going to do is, if that index that was passed in is equal to the current index I, and the type info of the current field type is optional, then we can return true. Okay. Otherwise, we'll just loop through all of the fields and we'll exit the loop. Okay, which will be unrolled. Okay, and basically will be converted into a series of these if statements, like if it was like this. Okay, given that none of them match in the case of a struct that doesn't have an optional field, we return false at the end. Okay. Now, the new part here is we're going to basically do the same thing, but now we're going to be using a switch with inline prong. Here, once again, we obtain the fields of the struct, and here we're returning the result of this switch. We're using the switch here as an expression. We're switching on the field index that was passed in here as a parameter, and here we go. We have the inline of this prong, which is a range which goes from 0 to fields.len minus 1. Because we're subtracting 1 because the ranges in switches are inclusive. Okay. And what do we do? This prong would then be expanded basically to each one of these indexes. Okay. So if in the case of our structs that only have 2 fields, they would basically, it would be like we had 2 prongs, one with, let's say here, 0, and the other one with 1. Okay, so it's basically would be transforming the code here marked with inline to those specific elements that we're trying to test directly. And here what we're going to do is, based on that index that was the matching index, we're going to once again call type info for the type of that field at that index, and we're going to see if it's optional. Okay, and that's what we are going to return. If the index falls out of these indexes here, then we just would fall to the else prong and we will return false. Okay. So that's basically how the inline prong, when you have a range in a switch, would work. It would automatically expand, so you don't have to do it yourself manually. And next up, we're going to see an example of another switch using inline, but this time it's going to be the inline else. And for that, we're going to be using a tag union here that only has these 2 fields, A and B, and they're of the type of the structs that we defined previously. Okay, and here we're defining what would be a method of this tag union called has impl. We're passing this parameter self. This is what basically makes it a method of the tag union. And we're going to return a bool. And what we're going to do is we're going to be switching once more over self. And normally when we would be switching over a tag union, well, we would have the different prongs for the different fields of the tag union. But in this case, we're going to make it easier using the inline else here, which basically would expand to the different fields of this tag union. And for each one, we would be capturing that struct type of each one of them. And then we would be calling this built-in called hasDecl, which lets us detect if a given type has a given declaration. And that's going to be of the type of S, which we are capturing over here. Okay. And the declaration that we're looking for, we're specifying right here. It's impl. Okay. So this should be true for this field, which has type A, and type A, that struct has the impl declaration function definition inside of it. So let's take a look at the output that we have so far. Let's run this. And here, when we see the examples of is-opt, we're using the for. In the case of A, we did have an optional, so it's true. In the case of B, we didn't have an optional, it's false. And we have exactly the same result using the inline, the switch with the inline range. Okay. And here we see the method of the tag union has impl using that built-in has decal. For A, it's true, and for B, it's false. Okay. Now we're going to be taking a look at the final test that we're going to see is that you can have a function in Zig that's a normal function. It doesn't have any comp time parameters, and inside of it you're going to see that it's basically normal Zig code. We're not using here an inline while, we're not using comp time vars or anything. But if this function can be evaluated and executed in a compile time context, which is the case with this fib function, we don't have any external side effects or system calls or anything like that. This can be then evaluated and executed at compile time by Zig. Okay, so this basically is our simple Fibonacci function here using the iterative approach instead of the recursive approach. And what we're doing is basically receiving a number here, and we're going to return that Fibonacci number in the Fibonacci sequence. Okay, so if back up here in main, what we're going to see is that here we're going to see an example of normal runtime context. We're calling here the function to print out whatever it returns. Okay, this is normal runtime execution. And here we're going to see how we can call it in a comp time context. Here what we're doing is we are prefixing this block with comp time. Okay, and what that means is that all of this, the body of the block is going to be evaluated at compile time. So this function call would happen at compile time, and basically all of this would be replaced with just the result of evaluating this function call. Okay, and it would be then assigned to ctfib, and then we print out here. Okay, and if we go out here to the output, we see that in effect the output is exactly the same, but in this case it was produced at compile time, and in this case it was produced at runtime. Okay, so the same function can be called in both contexts. Since this is just one function call, we could do this. Instead of using the block, we can just do the comp time and fib7, and it would be pretty much the same. Okay, this is an expression, a function call. It would be evaluated completely at compile time as required by using the comp time keyword. Okay, so let's save that and let's run it again, and there you go. We have the number 13, the 7th Fibonacci number. So there you have an example of how you don't have to have like a it's not mandatory to have like a special function with all these comp time features. You can have a normal function, and as long as it doesn't violate any of the rules of what can happen and what cannot happen at compile time, you can use your normal Zig function and have it evaluated at compile time. Okay, which is a really powerful feature. Once again, no need for macros, no need for preprocessors. It's all Zig, and you can decide if it's going to be evaluated at compile time or at runtime. Okay, so I hope you find this useful. Do the builder here. I'll see you in the next one.